and dot there. Okay, if you don't like that, you could make up your own visual representation. This is the standard one. Okay? All right, so g of 2 is 4. Okay? But it is a function, right? Because there's no place, is there any place where, because g of 2 is not 4 and 3, I'm not saying that. If it was, if I filled this in, then what? Then that's not a function. Because g of 2 is 3 and 4, that's no good. But I didn't draw that, I drew that. So it is a function. Okay? So it is a function. So even though it's a weird looking function, it is a function. Okay? So now, going back to my question, or let me go to my question now, and that is, if I asked you this, now the function, the question, the limit question is a little more interesting than it was in this case, because in this case it was obviously going to be 10. So it seems like, why do we need the concept of limit in this case? Just kind of superfluous. But here, the answer is different than the value at 2. The value at 2 is what? G of 2 is what? G of 2 is what? Is 4, right? The height at 2 is 4. But what's the limit? The limit is, if you play that game that we played over here, which is you take values closer and closer to 2, not closer and closer to 5, but closer and closer to 2, what would you guess it was? And I don't think anybody would guess that it would be 4 if you did that. In other words, if you were blind about what it was actually equal to at 2, you didn't know this picture. So imagine it's a game, and I know what this looks like, but you can only ask me questions. But you can't ask me exactly at 2. But you can ask as close as you want to 2. So nobody would ever end up guessing that it's equal to 4. Because you'd say, what is it here? And I'd say, it's this height. And then you'd say, what is it here? And I'd say, it's this height. And then you'd say, what is it here? And I'd say, it's this height. And then you'd come from this side, and you'd say, what is it here? And I'd say, at that height. And then you'd say, what is it here? And I'd say, at that height. And then I'd say, what is it here? And I'd say, at that height. Right? So you just keep getting closer and closer to 2, and what values would I get closer and closer to with my answer? 3, right? So you would never guess that it was 4. So the limit is not 4. The limit is what? What you would guess. That's what we mean by the limit. And what would you guess? 3. Okay, so you say, well, why are we playing this game and asking you to tell me what you would guess instead of what it actually is, right? You think this is a waste, right? But anyway, the answer is 3, right? So why, though? Why do we care about that? Because, think about it. The fact that it's 3 is telling you some important information. It's reporting to you some important information. What information? That it's getting closer and closer to 3. It doesn't mean that at 2 it's actually 3, but it's reporting this pattern to you. So it's useful for that purpose. It's reporting the pattern of what's happening near 2, but not exactly at 2. Okay, and that's the idea of a limit. So what's happening infinitely close to 2, but not at 2, if you let me use those words. Okay, infinitely close to 2, but not at 2. So again, what's the answer for the limit as x approaches 2 for this case? 3. What's the value of g at 2? 4. Let me repeat it again. What's the limit of g at 2? 3. But what's the value of g at 2? 4. Okay? So so you say, this is unnecessarily complicated, but it's not unnecessarily complicated because it's telling you the pattern. Close to 2, close to x getting to 2. Okay, so it's not unnecessary. It can be useful. All right? So now we have this statement as well. Okay, is that clear? All right? So that's called the limit. And limits are going to be useful for rates of change or for what we call the derivative. So, believe it or not. Just like the limit is just like a tool, but it will be a useful tool. So here's the first one that we had. The limit as x got closer to 3 was 5. Okay, and here are some other examples. So now let's get used to the notation here. So where does the function go in the limit notation? So where does the function go? After the word lim. Right? So where is the function in A? In part A. Or what is the function in part A? It's this whole thing. X cubed minus 8 over x minus 2. That's the function that we're talking about. And then we're talking about as x gets closer to something, in this case, x gets closer to what? 2. Okay, so the value on the x-axis of 2. Now, why do they present this problem to us? Why is this interesting? Because usually you would just put in x equals 2, right? And you could get the answer. Like here, when we go back to this, we didn't really need to do all of this. We could have just put in x equals 3 and gotten the answer of 5. So usually you would just replace x by the part that it's getting close to, right? And you'd be finished. But what happens when you do that here? If you replace x by 2, what do you get? On the top you get what? 0, and on the bottom you get what? 0. See, just replacing x by 2 gives you what we say is meaningless. That doesn't necessarily mean that the limit is meaningless. Okay, it just doesn't mean that. You can't know that yet. Okay, all you know so far is that if you, because that's not what the limit is asking about. It's not saying when x equals 2. It's saying when x is near 2. Okay, so, well, then I don't know what to do. Because I can put in x equals 2, but that doesn't do anything. Well, we can go back and do the table approach again. What does that mean, the table approach? Use values that are close to 2. But what's one value that's close to 2? 1.9. What's another? 1.99. What's another one? 2.1. 2.11. I'm sorry, 2.01. Right? And we could just do that. Now, I don't think we're going to get 0 over 0 in those cases. So we will get numbers. Okay? But that doesn't mean we're going to get an answer, like a good answer. It may not approach anything. Might just be we're getting random values out for y and there's no pattern. I don't know. And the same thing is going to be, well, let's see. So he says, this is not defined at 2. So we can't just substitute 2 in here and 2 in here. But we can do this. So let's not use our calculators. Let's just look at what he did. But you could put this into the calculator, in here and here, and do it. And if you put this one in, you get this. If you put this one in, you get this. If you put this one in, you get that. Put this one in, you get that. Put this one in, you get this. This one, this one, this one, this. So even though the function gives us 0 over 0. What about the limit? That's kind of interesting, right? So this is the first case where the limit is actually useful. Because what did we get? 0 over 0. We said we're not allowed to deal with that. So you might just throw up your hands and say, oh well, there's no answer. But somebody who has a little bit of perseverance is willing to kind of hammer this problem for a while, which probably wouldn't be me. If I had faced this, I would just have given up. I would have said, no, there's nothing, I'll just go on and do something else. But somebody didn't give up, and they said, well, let's look close to 2, right? And they did this, and they did this, and they got this, and they got this. Which is kind of remarkable. I would never have gone this far. I would have just given up. But what we discover is what? That it's getting closer and closer to 12. Right? I have to give somebody some credit for looking into this that carefully. The first person who did this. Right? So it turns out that even though the function is not defined at 2, somehow the function is approaching 12. Okay? So that certainly helps you to imagine what the graph looks like. Right? That helps you to imagine what the graph looks like. The graph is going to have a little circle when x equals 2. It's not going to be defined at x equals 2. But close to 2, it's going to be closer and the height is going to be closer and closer to 12. Which is sort of surprising. Okay. Now I guess the reason somebody actually pushed through on this is that it was arising in some physical problem, and they really wanted to know the answer, and so they weren't going to just give up. It wasn't just like a simple math problem. It was arising in terms of some actual calculation they needed to do, and so they pushed it. And he says, we notice that as x approaches 2 from either side, f of x appears to be approaching 12. So let's just pay attention to this phrase for a second. From either side. Do you understand that? From this side, what is f getting close to? 12. And from this side, what is x getting close to? 12. Now, if this side happened to be getting closer, if we came in from this side and it was like 15, and this side it was 10, then we wouldn't say that the limit is 12. Or we wouldn't say it was 10 and we wouldn't say it was 15. Okay? So in order for it to say it's something, like to say that it's 12, it has to be getting closer to 12 from the right of 2, from bigger than 2, and from the left of 2, from the less than 2. They both have to give you 12 in order for us to use that language. In order for us to say the limit is 12. Okay? Is that clear? If we got two different numbers, one from the left and one from the right, we can't say that we'll say that the limit does not exist. Okay, so if we got from this side, we got 10, and from this side we got 15, we just say the limit doesn't exist. Okay? But we'll still actually say one more thing, and that is if we got from this side it was 10, and from this side it was 15, we'll say that the limit from the right is 10, and the limit from the left, no, sorry, the other way around. Yeah. And the limit from the left is 15. Okay? So we will say that, even though we'll say the general limit doesn't exist. So that, or the two-sided limit doesn't exist, but the one-sided limits exist. Okay? So we'll use that language as well. we got 12 in this case. And this one is another one. You also get 0 over 0, but if you do this again, you get what as the answer? 2. Right? These numbers are both getting close to 2. All right? Here's the notation. I said we use this. We can say f of x approaches L as x approaches A. F of x approaches L as x approaches A. And you can also write it like this. Okay, I didn't write it like that actually. But you can also write it like this. Okay, then we also have this one. Does not exist. Okay, and when you do that for an answer in the homework, they tell you to write capital D N E. Does not exist. D N E. Okay, so sometimes the limit doesn't exist, and they want you to write D N E in capital letters. Okay? Okay, how about these? All right, now what I'd like you to do right now is, okay, let's do the same thing I did last time in my class, which was to change the subject completely, just for fun. And I said, anybody want to bet me that 2 people in this room have the same birthday? How many people are in the room? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. About maybe 25 people. So anybody want to bet that 2 people? And I don't know. Haven't been able to check anybody's birthday, so I have no idea. But does anyone want to bet me? I'll bet you 500 yen that there are 2 people in the room that have the same birthday. Anybody want to bet me? There's only about 25 people here. So there's a chance high or low. What would you say? Low, right? So if you say low, then you should be willing to bet me, right? Right? I don't have any inside information here. I didn't check anybody's birthdays. I have no idea when anybody was born. Birthday means what day of the year. Right? Nobody wants to bet? Really? I'm not guaranteed to win at all.
I'm betting.
Oh, he'll bet. Actually, I don't want to bet. I don't actually want to bet. I'm not sure how many people are in this room. I think there's probably 25, but I'm not sure. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh yeah, there's more than 25, okay. Actually, I should bet. If I'm smart, I'll bet. But I'll lower the bet to 100 yen. Want to bet? 100 yen?
200 yen.
No, I don't want to. I'll do 100. Okay, 100 yen, we have a wager. I say that there are 2 people in the room that have the same birthday. Now, I'll give you a little hint. I did this yesterday in my same class, about the same number of people. And an amazing result happened. There were 4 pairs of people that had the same birthday. Not just one pair. And not only that, but the first person I asked had the same birthday as me. So, it was pretty amazing. Now, again, I happened to do the same thing today in a different class. And there were 3 pairs of people that had the same. This is really weird because sometimes when I do this, it doesn't work. And sometimes it works and you get 1 pair. And rarely, sometimes you'll get 2. Yesterday I got 4 and today I got 3. The chances are nobody in this class will be, but that's wrong thinking, right? Chances. When I say chances are nobody will be in this class